Hey everyone, and welcome to today's Explainer. Today, we are popping the hood and looking at the absolute fundamental core of cloud network traffic management. We're talking about the hidden plumbing that makes split-second routing possible across the internet. Seriously, every single time you load a web page, stream a movie, or send a quick message, data is traveling across the globe in an instant. But how do those tiny packets of data know exactly where they're supposed to go?
It's a pretty fascinating question, right? When millions, literally millions of data packets hit a network switch every single second, how does it know exactly where to send them without missing a beat? Think of a network switch like this relentless, ultra-fast traffic cop working behind the scenes. Now, this traffic cop doesn't have time to stop, sip a coffee, and think about it. It needs a perfectly structured, rigid set of instructions to direct that massive flow of the internet instantly. So, to understand how our traffic cop works, here's our roadmap for today. 1. Meet the flow table. 2. Decoding the rulebook. 3. Exceptions and special actions. And 4. We'll look at a real-world packet example.
All right, let's jump right into Section 1, Meet the Flow Table, the ultimate network rulebook.
So, what actually is a flow table? By definition, it's a set of network rules that match incoming packet fields to specific forwarding actions. Think of it as a massive, high-speed checklist. When a piece of data arrives, the switch immediately consults this checklist to figure out exactly what that packet's destiny is going to be.
Now, here's a sample flow table pulled straight from our source material. I know, at first glance, it just looks like a dense block of numbers and tech jargon. Don't let it intimidate you, though, because underneath all that complex-looking data, the fundamental structure here is incredibly simple and, honestly, quite elegant.
Let's break it down. On the left side, we have the match fields, basically the specific conditions or traits we're looking for in a data packet. And on the right side, we have the actions, which dictate the resulting behavior. It's just a classic if this, then that scenario. If a packet has a certain characteristic on the left, the switch performs the exact action on the right. Simple as that.
Moving right along to Section 2, Decoding the Rulebook, focusing on IPs and MACs.
First up, we've got rules based on the source MAC address. Now, a MAC address is just the physical, hardware-level identifier of a device. According to our sample flow table, if a packet arrives and its source MAC address ends in 5E, the action is to forward that packet out of output port 2. If it ends in 5F, boom, it goes out of output port 3. This is direct, physical-level routing at its finest.
But you know, the flow table goes way beyond just physical hardware. It uses IP addresses too. The table can look at where the packet originated, its source IP, or where it's trying to go, the destination IP. For instance, if the source IP is 192.168.1.10, the packet gets routed to port 4. Or actually, let's say the switch reads the destination IP as 10.0.0.1. It sends it to port 1. It really shows how flexible the switch can be, reading totally different layers of a packet's identity to route traffic seamlessly.
Which brings us to Section 3, Exceptions and Special Actions, because it's not always about simple forwarding.
Sometimes, the network switch doesn't just blindly wave every packet through. Sometimes, the required action is an exception. We've got two key special actions in our rulebook here. The first is drop packet, which literally means exactly what it sounds like. The switch just destroys or ignores the packet entirely. It goes nowhere. The second is send to controller. This is basically an escalation. It means the switch is passing the packet up the chain of command to a higher authority, the software-defined networking or SDN controller for further processing.
Looking at our source document, we can see exactly how this plays out. If the source MAC ends in 5E, the instruction is to drop the packet cold. If the source IP is 192.168.130, the switch has to send it to the controller. It's an absolutely crucial feature, because these rules allow network admins to dynamically block malicious hardware or automatically escalate any suspicious, unknown traffic.
All right, Section 4. Let's put all this theory into practice with a real-world packet example. Picture this. A brand new, totally wild mystery data packet has just hit our switch, and it brings with it three very distinct identifying characteristics. Its source MAC ends in 5F. Its source IP is 192.168.1.20, and its destination IP is 10.0.0.2.
The exact millisecond this packet hits the switch, the internal scanning process kicks off. The switch immediately starts comparing the packet's data against the flow table. It checks the MAC address. Check. It checks the source IP. Check. It checks the destination IP.
But hold on, Houston, we have a major complication. Our single mystery packet actually matches multiple different rules in the table at the exact same time.
Its MAC address says to send it to port 3, its source IP says send it to port 5, and its destination IP says send it to port 2. So what does a switch do when it's literally being pulled in 3 different directions?
Well, the source material gives us the definitive answer. I'm going to read it directly. The first rule matches the source MAC address, so the packet is forwarded out of port 3. It sounds incredibly simple, right? But the implication behind this is absolutely massive.
And that brings us to the golden rule of the network switch. The forwarding decision is always based on the very first matching rule it encounters. That's it. The order of the rules in the flow table is quite literally just as important as the rules themselves. It operates on a very strict top-down hierarchy. So because the packet matched the MAC address rule first, you're probably wondering, what about those other valid matches? Well, the source IP match telling it to go to port 5? Ignored. Completely ignored. The destination IP match telling it to go to port 2? Also ignored. Because they appeared lower down in the flow table, they have zero effect on the forwarding decision in this case whatsoever.
1. That is the number of rules a packet can actually follow for a forwarding decision in this context. The entire architecture of cloud networking relies on this strict number 1 hierarchy to avoid total routing chaos. Think about it. If switches tried to execute multiple conflicting routing rules all at once, the internet would just grind to a halt. Prioritization is literally everything.
Which leaves us with this final thought to chew on. We just walked through how this strict sequential logic beautifully handles a single packet on a tiny 8-rule table. But can you imagine the scale, the speed, and the massive flow tables required to power the entire cloud computing ecosystem? We're talking billions of rules executing in fractions of a millisecond, all working together to keep our digital world flowing perfectly. Really gives you a whole new appreciation for the unseen architecture of the internet, doesn't it? Thanks for joining me on this explainer, and keep learning.